Okay, good morning. How's project 2 going? Questions? Okay. Let's see, we are on lecture 27. Yes.
So I know there's a design requirement for the lower corner of the drag bucket. Is there also a requirement for the upper corner? I don't know if that's been asked before, but like, is there a certain CL max that you want us to achieve, or it doesn't matter?
So any requirement for upper corner, there is no requirement. It kind of gets decided by the thickness for the most part. If you read that paper also, that's how it turns out to be. So no explicit requirement. And CL max, I don't know, I don't think I gave any requirement, right? So whatever is you get, you can improve CL max by playing around with the recovery shape, but I'm not giving any requirement.
Okay. The reason I asked that is because I think when it asks us to specify the transition, the 50% in part A, it says for the low drag region, so that would just be between the lower end of the drag bucket and whatever the upper end happens to be.
Yes. So somewhere near the middle of the drag bucket, both upper and lower surface will have laminar flow at least until the end of the favorable gradient, which is what you're going to set, right, with your in the question, as required in the question.
Okay. And then I guess one more thing. I was having trouble. It was fine for the 50% or favorable gradient for positive angles of attack, but I noticed that negative angles of attack, my lower surface I had a hard time getting a favorable gradient. Like, it would be adverse.
Yeah, at negative angles of attack. So the question is, negative angles of attack, you're not getting favorable gradient on the lower surface. Yeah. That's when you fall out of the drag bucket.
Okay.
That's sort of associated with getting out of the drag bucket.
Okay. Even if my drag bucket goes down to like -2 degrees, or?
And at -2 degrees, up to the bottom of the drag bucket, lower corner of the drag bucket, you should get laminar flow on the lower surface. I mean, that's why there is a drag bucket up to that point. Okay. Okay. So today we're going to do one topic in thin airfoil theory. So in the end of the last class, I listed these as items to do in thin airfoil theory, right? So today we are going to do this part, and I've kind of fallen behind by about one class or so. So I'm going to see if I can record these either this week or early next week and have it as a recorded class, because I think we're going to be short on time. Okay, with that, let's talk about an example. So, thin airfoil theory, the derivation is kind of long and complicated, and it all starts to make sense if you sit down and work through it. But in the end, maybe the question of interest is, if you're given a camber line, how do you calculate the aerodynamic properties, right? So for that, we're going to take a simple example that's there in many textbooks to illustrate thin airfoil theory. And this shape is a parabolic camber line. So it's something like this. So It's a parabola from 0 to 1, x equals 0 to 1, and at the middle of the chord, half chord, it has got the maximum height, and that maximum height is Zm. So this is x-axis and this is z-axis, and Zm is the maximum Zmax. So the equation of this parabola is z is 2Zm times x over c minus x over c squared. So just a simple shape for illustration. We take the derivative, we'll need dz dx in so many places in thin airfoil theory. So dz dx turns out to be this. So easiest to work in theta coordinates in thin airfoil theory. So let's convert the theta coordinates, let's convert the x to theta coordinates using this transformation, right? The same transformation that we used in thin airfoil theory. X equals c over 2 times 1 minus cosine theta. And dz dx is this. We convert this to in theta coordinates, and you get 2 times Zm over c times cosine theta. Okay, so we got these things. Now we can plug them into the thin airfoil theory equations and get A0, A1, A2, A3 and so on. Okay, let me see if I have those for reference from the previous. Yeah, so from the last lecture we saw that this is the expression for A0. Okay, integral 0 to pi dz dx in terms of theta d theta. So we plug that in here, and if you plug dz dx in terms of theta, which is this, and integrate from 0 to pi, this integral becomes pi, and so this integral becomes 0 because it's integral of cosine theta from 0 to pi. So the result is A0 is just alpha. Okay, now we still need to get the other A1 and A2 and all that. So again, going back to the notes from the last class, we derived that AN from 26-11, page 26-11, AN is 2 over pi integral 0 to pi dz dx in terms of theta times cosine of n theta. So whatever n you want, you do cosine of n times theta in the integral. Okay, so if we do that, for any n greater than 1, right? So let's take A1. So cosine of n theta is just cosine theta, and we already had dz dx from the previous page, so you plug all that in. A1 turns out to be 2 times Zm over c. And then when you go to all the other a's, something really neat happens, and this is all, I mean, this is all the result of choosing a great transformation, right? It's only, the simplification happens because somebody thought through this really well and came up with a good transformation. So A2 is dz dx times cosine 2 theta in the integral, right? Now if you integrate 0 to pi cosine n theta times cosine m theta, if n and m are different, answer will always be 0. So A2 will be 0, and that same reason all the a's after 2 and above, all the a's will become 0 for this particular camber line, which is kind of remarkable how things simplify if you choose the correct transformations. So that's it. With this, that's the power of thin airfoil theory. We have solved the results for a parabolic camber line. So what we get here is alpha 0 lift in radians is minus Zm over c. So CL lift coefficient is 2 pi times alpha minus alpha 0 lift, so that turns out to be this. Pitching moment about the quarter chord, which is also the aerodynamic center, which is also Cm0, is minus half pi times Vm over C. And so the good thing about this is we can now see what are the trends due to increase in camber. When you change the max camber value, what happens? And even though this is for a parabolic camber line, the general idea is the same for any camber shape. When you increase camber, keeping the shape, the form of the camber line the same, this is what happens. Parabolic camber is just easy to analyze, sort of analytically with thin airfoil theory. So let's talk about the trends. Okay, so CL versus alpha is a curve like this. The slope is 2 pi per radian, and this angle is alpha 0 lift. Right? Obviously, the viscous behavior will be where it deviates from this linear behavior and reaches a maximum and stalls. But what happens when you increase camber? This curve shifts to the left because the alpha 0 lift becomes progressively more negative. And then if you look at pitching moment about the quarter chord, pitching moment coefficient, thin airfoil theory gives this. Because of viscous effects, you might have deviations. But when you increase the camber, the pitching moment will become more and more negative, because that's what we saw in this page, right? As you increase Zm, pitching moment becomes, coefficient of pitching moment about the quarter chord becomes more negative. Okay, so that's this simple example, distills all those complicated looking equations and says, this is what you can do. So you can actually do this for any camber line. If it's a camber line that's not an equation, if you've got a bunch of points, you can do it numerically, and there are some books give them method for how to do that numerically. Okay. So, like I said, these other two topics, ideal angle of attack and effect of flap deflection, I'll work on recording those in an offline session, or if it turns out there's a studio available, studio classroom, then I'll send a message and those who are able to attend can come. So we'll go to something else, some other topic, and that is a discussion on multi-element airfoils. Okay, so on Moodle I've put some reading material, right? I think it's been there from the beginning of the semester. And one of those papers is a paper by A.M.O. Smith titled High Lift Aerodynamics. So A.M.O. Smith was an aerodynamicist for McDonnell Douglas, I believe, I think so, McDonnell Douglas. And he has made a lot of contributions. So he was in the industry, so he was actually designing a lot of airplane and wing aerodynamics. But he also wrote this paper that attempts to explain why multi-element airfoils and why, how do you achieve high lift. So firstly, what is multi-element airfoil? A multi-element airfoil is an airfoil that's got two or more elements. Okay, so it's something like this. If you have an airfoil with a slotted flap, for example. So this is a slotted flap. Single slotted flap, I think is called. And there are many versions of these. One of the simplest versions is you have this flap on a simple hinge And if it's an external hinge, when you extend the flap, this whole thing will rotate and form a multi-element airfoil. And in many cases, most airplanes, you can also tuck it in. When the flap is fully retracted, it looks like a regular single element airfoil. There will be some gaps, but for the most part, it behaves like a single element airfoil. Now, some of these flaps are also on tracks. So if you have a simple slotted flap on a hinge, the movement is restricted, right? It's the angle and the extension are all controlled by this. So sometimes to get very good high lift characteristics, you want it to go back and then you want it to tilt down. And you want it to do things like that. And so then you do something called a more complicated flap called a Fowler flap, where there is a track. And this flap will go on this track, and as it goes out, the track geometry will be designed so that at various points it'll angle downwards. And so this will extend the chord and also change the deflection. And then like that you can also have a slat, a leading edge slat. So this is a surface that's tucked in at the leading edge, and then it comes out, pops out when you want high lift. Either almost all the time it is pilot controlled, so the pilot actuates the slat. But there are a few airplane designs, and I don't think they do this anymore, but back in 1920s and 30s, there were a few airplanes where, like the de Havilland Tiger Moth, I think is an example, where the slats are spring loaded, and at high angle of attack, there will be a lot of suction here, and the suction will cause the slats to automatically pop out exactly when it's needed, right? It's at high angle of attack that you need it, and so that will pop out. And when the suction goes away, the spring will pull it back. So it was like the pilot didn't have to do anything, which was a pretty clever idea. So why do these things work? How do these multi-element airfoils generate high lift? So that's what Amos Smith's paper attempts to explain, and I think it's one of the best explanations of why multi-element airfoils work. And even that is fairly complicated. So, but he's tried to distill it into 5 primary effects. And these are the 5 primary effects. Some of these have overlapping effects, so for example, the slat effect and the circulation effect and the dumping effect, they're not completely unique. It's like a little Venn diagram where there is some of the explanations are, some things work because of both this and this and this, like that. Anyway, so let's take these 5 effects and think about what they do. And this is all based on Amos Smith's paper, so I recommend that you read it. It's a long paper, but it's a good paper. It's worth it. Some of the thinking and the explanation is from the era in which the paper was written. So back in the 1950s and 60s, they were doing a lot of things by hand and by some analytical methods. So, some of the paper will be about that. You can avoid getting bogged down in those things and just try to get the big picture. So slat effect, right? So here is an airfoil at a high angle of attack close to stall. And we know that stall occurs because boundary layer separates on the upper surface near the trailing edge. But why does the boundary layer separate? It happens because at higher angle of attack, the stagnation point moves, it's not at the leading edge, it moves into the lower surface a little bit. And so the flow comes around and has to accelerate around the curved leading edge. So as it goes around the leading edge, it goes at very high speed. So maybe 1.2 or 1.3 times V infinity, right? And high velocity means low pressure from Bernoulli's theorem. So if you draw a CP diagram, you get a suction peak, and you've probably seen this in X-foil, right? So a suction peak is basically some kind of a peak near the leading edge. This is all suction, so it's called suction peak. But downstream of the suction peak, there is a big adverse pressure gradient. And so the boundary layer, as it's going past this adverse pressure gradient, by the time it comes here, it loses momentum close to the surface, and there's reverse flow and there's separation, and that's what causes this separation. So a slat is able to postpone this separation. So what happens to the CL alpha curve is you take this airfoil, and without a slat, the CL alpha curve is like this. But when you put a slat, the CL alpha curve gets extended. So this doesn't shift the CL alpha curve. A flap will shift the CL alpha curve, as we'll see when I finish that discussion in thin airfoil theory. But a slat just extends this. It pulls this up to a higher CL and higher alpha, and then eventually even that stalls. But you get this much extra lifting capability. So why does that happen? So Amos Smith calls this the slat effect. So what is happening is the slat is an airfoil here, and that's generating lift, right? The slat is an airfoil, and when it's pulled out like that, that generates a small amount of lift. And remember, you can replace any lifting object, any aerodynamically lifting object, with a circulation, with a vortex. So Amos Smith says, hey, let's, for purposes of understanding why a slat works, let's replace this by some vortex, just for purposes of mental exercise kind of thing. This vortex will cause a flow in this direction. And so that is opposite to the flow that is due to the acceleration of the regular leading edge flow, right? So before, without the slat, if you had a suction peak like this, because you have opposite flow induced by the slat, the net velocity along the surface here reduces, and so the suction also reduces, and so the suction peak is softened with the slat. And because of that, the separation on the main element, separation here, is postponed, and so you get higher CL max and higher alpha. So in short, that's the slat effect. So now let's talk about circulation effect. So sometimes you have an aft element, right? This can be a flap. Usually the flap will be much smaller than the main element, but in some applications it doesn't have to be. They may be of the same size, like in a race car wing. You could have a main element and a flap of approximately the same size. Maybe this will be 80% of this size or something, but in general, why does having an aft element help with achieving high lift? So same kind of mental picture to help conceptualize why this flap helps. So this flap is also a lifting airfoil, so we can replace it with a vortex for aerodynamic purposes, just for thinking about how this works. And this vortex causes some sort of an upwash here. When when you consider the aerodynamics on this airfoil, if there is an upwash, when you enforce zero normal flow through the airfoil, this part will get more heavily loaded. In other words, it'll produce more lift. So if this is the CP distribution on the main element, So if this is a CP distribution without the aft element, so let's call this the main element and the aft element. With the aft element, this portion of the airfoil produces more lift. And so that is what he calls circulation effect from the aft element or the aft vortex. So the third effect is called dumping effect, and this has got similarities to the circulation effect. Okay, it's somewhat similar to the circulation effect, and it tries to address the same thing. Why does an aft element help? And so this is another effect of having the aft element. And what this does is the aft element causes an increase in flow speed near the lower trailing edge of the main element, because this is like a vortex, right? So if you position this aft element correctly, you will have an increase in flow speed here. And remember, from kata condition, if the velocity on the lower surface trailing edge should be the same as the velocity on the upper surface trailing edge. So if you have this as the CP distribution on the main element, this is the velocity without the aft element. With the aft element, there is an increase in speed, so this moves up here. And so you get a higher V trailing edge. And because you get a higher V trailing edge, if you have a suction peak here, without the flap, it would have had to come all the way down here, so the big adverse pressure gradient. With the flap, because the V trailing edge moves up, the amount of adverse pressure gradient is decreased. So separation on the main element is postponed, and so the main element is able to generate more lift before it starts stalling. Okay, so some more sort of mental exercises, all again from Amos Smith's paper. So he's posed the question, well, what will happen if you put a cylinder below the trailing edge of the main element? Okay, so cylinder will cause a speed up, right, in this region. That will cause something like a dumping effect. I mean, nobody would actually go and put a cylinder because that will cause a lot of drag, but just as a mental exercise in potential flow, what will happen? That's the question here. But depending on how you move the cylinder, you will get some circulation effect or some dumping effect, or more of circulation, more of dumping of that sort. So here you'll get more dumping effect because you increase the flow speed, but you're not causing any induced flow in this direction, right? In the upward direction will help circulation effect. But if you move the circle or cylinder towards some position here, you'll not only increase flow speed, you'll also cause a flow like this that will increase the circulation, that will cause circulation effect. So the point of this is you have the circulation and dumping, but by moving the aft element around, in this case it's a cylinder to help think about it more easily, you can tailor the upwash on the trailing edge and the increase in flow speed. Okay, so all of this is fine, but one of the things you have to think about when you do multi-element airfoils is anytime you increase aft loading, you also make the pitching moment more negative. And sometimes that could cause some undesirable effects like more trim drag or something like that. But this is also true for single element airfoils. So there are airfoils like this S1223 high lift airfoil designed by Michael Selig, where they've designed the single element airfoil to have a lot of aft loading. So normal airfoil will look like this. A high lift, an airfoil with high aft loading will almost look like this. It'll have a trailing edge that's almost curved to cause a lot of lift at the trailing edge. And the nice thing about a lift at the trailing edge is, if the normal airfoil is like this, the high aft loaded airfoil will be like this. So you reduce the amount of adverse pressure gradient. So you can get more CL max, but then all this aft loading is also making the pitching moment more negative. So there are trade-offs, right? So it's not like it's always this is the way to go. Okay, the fourth effect is called off the surface pressure recovery. So Amos Smith poses the question, suppose you have a big airfoil, single element airfoil like this. If you want high lift, is it better to replace this single element with two elements like this of approximately the same total chord? In other words, is it better to split this up into two airfoils, and will it help? So let's take this big single element airfoil first. If you want to increase lift, you have to push up the upper surface pressure distribution, right? And after a point, if you start pushing up the upper surface pressure distribution, you're going to have more adverse pressure gradient in the rear. And after some time, that's going to max out your lift capability because the adverse pressure gradient will separate the flow. Now, if you replace it with two elements, the argument goes, and I think this is correct in practice too. So it turns out, because of the circulation and dumping effect, the front element trailing edge velocity is not near 1, it is much higher than 1. And so you can design the front element to say, okay, trailing edge velocity is here, now I'm going to design this pressure distribution, and there is adverse pressure gradient, but this pressure eventually comes to near atmospheric pressure only around this point. So there is pressure recovery. You can make an aggressive pressure recovery here and not separate the flow, and have additional pressure recovery occur along the wake of the main element that flows on top of the aft element. So part of the pressure recovery for the main element happens partly in the wake region, and it turns out the wake region can tolerate greater adverse pressure gradient because it's not going along a surface. If anytime there's boundary layer along the surface, there's skin friction which takes away momentum. But a wake is not bounded by a surface, right? At least as long as the wake doesn't touch this. So it can tolerate greater adverse pressure gradients, and therefore you can design this to have greater lift than if you had a single airfoil that was of a longer chord. So while we are on this topic, it's maybe a good time to introduce this or give a very quick explanation of this phenomenon called wake bursting. So wake bursting is similar to separation on boundary layers. Just like you can have a boundary layer that separates, a wake also can burst and cause some bad effects. So let's see what that is. So first let's see what separation is, right? We have seen this before. A separated flow is where you have a boundary layer on a surface like an airfoil, and then as it comes to the back, if there's adverse pressure gradient and momentum loss, the portion of the boundary layer near the surface might have reverse flow, and that's separated boundary layer. And when that happens, the displacement thickness kind of suddenly becomes large and you have separated flow. That's boundary layer separation. Wake bursting is a similar phenomenon, but it occurs in wakes. So what is a wake? So let's take this main element and flap element, and the main element has the wake going like this. It's going on top of the flap, but it's not touching the flap. So if you look at a cross section here, the wake has a momentum deficit like this. Right? That's the momentum deficit that captures all that. Has this loss in momentum is equal to the drag of the main element. Now, when this wake goes over a flap, the flap also has adverse pressure gradient. So whatever adverse pressure gradient is felt on the flap, it's going to be felt a little bit up above the flap too, which is where the wake is going. Right? So the wake also experiences some adverse pressure gradient, and if it exceeds a certain amount, it will take away momentum from this wake. The wake already has a momentum deficit, and it will continue to take momentum out of it some more until the wake also has reversed flow. So this wake doesn't have reverse flow, right? It only has slower velocity. But when the wake bursts, there is reverse flow in the wake, and that's called wake bursting. And just like the boundary layer sort of suddenly becomes large in thickness, the wake will also become large in thickness, and this is called wake bursting. And this is one of the limiting factors for how much you can push the wake and make it go past adverse pressure gradient. So even the wake can't tolerate more than a certain amount of adverse pressure gradient. Okay, and then the last effect for multi-element airfoils is this thing called fresh boundary layer effect. So here we go back to this comparison of taking a single airfoil, a big chord airfoil, and seeing, is this better, or is it better to split it up into two small elements of approximately the same chord. So another advantage of doing this is, if you have a single airfoil, this boundary layer that's been flowing from the leading edge all the way down here, and now it's experiencing adverse pressure gradient, and it's going to separate. But for the same amount of adverse pressure gradient, if you split it up into two, this boundary layer is the one that experiences that adverse pressure gradient, and it's a smaller length boundary layer, right? It only started here, as opposed to this far away in the single element airfoil. So this is like a fresh boundary layer, and it's not lost as much momentum as this longer boundary layer that if you had a single airfoil. And as a result, I mean, in a if you want to think of it in a simple manner, this is less tired, so to speak. It's lost less momentum, right? So it's able to negotiate larger adverse pressure gradient because it's a fresh boundary layer compared to this one. And so all these effects put together help multi-element airfoils generate higher lift than a single element airfoil. In many situations, it's hard to separate out and say this effect is exactly what is helping. All these effects together work to get higher lift. Okay, so do read that paper. I mean, the semester is coming to an end quickly, so I understand you'll all have various demands on your time, but maybe save it up for after the course and read it during your break or something. It's a good paper to read if you're very curious about how various aerodynamic devices work. It gives intuition, and that's what is sometimes hard in complicated flows. you can always put some geometry into some CFD code and press a button and it will give you an answer. But unless you understand why something happens, at least some very vague idea of why something happens, you won't be able to go and harness it when you design some new device or something new. Okay. Any general questions? So we're going to move on to a new topic, and it's not lecture 26. And this is sort of the last topic in the course, and here I'm going to try to explain the use of conformal mapping for airfoil aerodynamics. So broadly, this is in 4 subtopics. Review of complex variables, which I'll leave for you to do on your own. I've put some notes on Moodle. It's been there for some time. It's just like 2 or 3 pages that basically reviews complex variables. If you haven't touched it in a long time, it'll be a good thing to go and look through it. We'll talk about analytic functions and Cauchy-Riemann equations. We'll talk about mapping, and then finally we'll come to Joukowsky airfoils. And there are many more advanced topics that one could do in this. For example, the Profoil code, the whole inverse design code, is built on conformal mapping. So it's got a lot of really powerful applications. And if you want to take more time and digest this, most of my notes that I'm going to use here are from 3 chapters from this book, Principles of Ideal Fluid Aerodynamics by Karam Chetty, which is there in the library too. It's one of those really solid books. It's pretty math heavy, but it's got really good stuff. It's from maybe 40 years back at least. So, like I said, basics of complex variables, refer to the pre-prepared notes. We'll jump straight to functions of a complex variable. What is a function, right? So, let me see if I can pull that up. So here is the stuff I'm talking about. This is Amos Smith's paper, and this is a review of complex variables. It's just a couple of pages of handwritten notes. But it really basically starts from very simple stuff like what is an imaginary number, and very, very quickly it goes about how do you add, how do you subtract, just review. And what is a geometrical interpretation, how do you write it in polar coordinates, and then what is the exponential form of a complex variable, what is the meaning of product of 2 complex variables, and like basically 3 pages. So it's a very quick review. I'm sure you've done all this in math, but depending on when you did it, some of it might have, maybe it's not something that you remember clearly. It's, so let's talk about functions of a complex variable. So basically, if you have a complex variable z, and for every value of z, if you can get another complex number, zeta, so this is zeta, it's I'm probably not writing it too well. So if you have some rule that for every value of z you get a zeta, then that is a complex function. It's just like y equals f of x for a simple real function. You put in an x and you get a y, right? Like that, you put in a complex number, you get another complex number. So the main complex number z is x plus iy, and zeta, we're going to write it as psi plus I eta, right? This is symbol psi, this is the real part, and eta is the imaginary part. So that means both the real and the imaginary part are functions of z. So psi is a function of z, which means it will depend on x and y, and eta is another function of z, which means eta is function of x, y, and so you can write the new complex number as psi function of xy plus eta I eta function of xy. So graphically you might have maybe something that looks like this. The psi, if you plot the xy coordinates, the psi might be a contour like a function like this, function of two variables xy, and the eta might be another function like this. So this is what is a function of a complex variable. Now among complex variables or among complex functions, the ones that are of interest for whatever we are doing and in many fields are these things called analytic functions. So they are not analytical, they are analytic functions, and they have a very specific meaning. How many of you have done some complex variables at grad level? Oh, you have? Here at NC State or somewhere else?
Just like as part of CFD.
Okay. The CFD course here, you took a, okay, they talk about complex variables, I guess for gridding, for generating grids or something?
Yeah.
Okay. There is also a course in the math department on complex variables. But I think the thing I've heard is they quickly go off into some very esoteric stuff that after some time most of us engineers will have a hard time connecting it with anything that we want to do. Whereas here, this is all, in the end, it will tie up to airfoils very beautifully. I mean, you just have to persist until that time, and then it'll like, wow, how did they even go from here to there? But somebody did. So the functions, complex functions that are of interest are those that are differentiable, and these are called analytic functions, and differentiable automatically implies continuity. So let's see what they are. So we have this complex function zeta equals zeta of z, right? So this function is said to be differentiable at some point z if, as a neighboring point z1 approaches the limit z minus z1, or actually it should be approaches the limit z going toward z1 going towards z. We'll draw some pictures to make this clearer. So in the limit as z1 goes to z, the derivative should exist. The derivative being zeta at z1 minus zeta at z divided by z1 minus z. This derivative should exist. So the derivative at zeta, or the derivative of zeta at z is denoted by d zeta dz or zeta prime, and that is, the definition is in the limit as z1 goes to z, zeta at z1 minus zeta at z divided by z1 minus z. So essentially this is the derivative. So this is kind of very similar to real functions. Okay, real functions are something we have been doing so long that usually it's intuitive. So in a real function y equals f of x, you have some curve, and at some point x, the derivative is delta y over delta x as delta x goes to a very small value, pretty much 0, as it tends to 0, right? So that gives the tangent to this curve, that's the derivative. A complex function is more complicated because it's a function of two variables, right? You have in the z plane, you have the real part which is x and the imaginary part which is y. And if you have a point z, you can now take the derivative of z1 take the derivative of at z, which is value at z1 minus value at z divided by z1 minus z, right? But now the z1 can be in multiple directions. Here there was only, delta x is only this way or this way. But here you can have z1 here, z1 here, z1 here. Any of those points are neighboring points. So to avoid that, the condition for a complex function to be differentiable at point z is that that limit that we just defined, as delta z goes to 0, delta zeta over delta z should be the same no matter which direction z1 approaches z. So in other words, that derivative should be the same whether you take this, this or this. As long as everything is in the neighborhood. This is all small distances, right? I've drawn it large. So that is the condition for an analytic function. Okay. So these are the functions that are of interest. So for any complex domain Z, the points where zeta of Z is analytic, these are called regular points. But sometimes there will be points at which the function is not analytic. It's like even when we did vortex and source and all that, we saw that except at the source or the vortex, some laws are satisfied, right? Like continuity and what else? I think continuity. So though the continuity is satisfied everywhere except at the point source. So the point source is a singularity, everywhere else the flow is correct, right? The flow is satisfying regular laws. Like that, in the flows of in the complex functions of interest that we'll be looking at, there'll be some points called singular points. So at those points, the functions will not be analytic. Everywhere else it will be analytic. Okay, so just let's quickly review rules for derivatives of complex functions. These are very similar to real derivatives, real function derivatives. So d over dz of sum of two functions f and g is df dz plus dg dz. Okay, straightforward stuff. D over dz of f times g, just like a real function, is f prime g plus f times g prime. Okay, and then d over dz of f divided by g is f prime g minus g prime f over g squared, as long as g of z is not equal to 0. So this is just simple, regular, just like real functions. And then we have this other rule that says if f of z is analytic, not f, sorry, if zeta of z is analytic and you have another analytic function which is w of zeta, this is another analytic function, then w of zeta of z, if you can write that as g of z, that is also analytic. In other words, an analytic function of another analytic function is also analytic. Okay, so these are some rules. I'm actually sort of taking only the main points and trying to distill it down to, so that we reach some place connected to airfoils, and that's really the main interest. If you're curious about this, it's really worthwhile taking Karam Chetty's book, or many other books also discuss this, and really sitting down with it and going through it in a more slow fashion. This sort of stuff, unfortunately, is not taught these days at all. Like most aerodynamics books, they have stopped talking about complex variables and conformal mapping altogether. I think it's all because you have many tools like Xfoil. Numerical methods have sort of taken over, but I think it's still important. There's still a lot to be learned by going back to these things. Okay, so something important that comes out of all this is called Cauchy-Riemann conditions. So here we take a complex function zeta of z, which again we called same as before, which is psi plus I eta, right? And this is our complex domain. This is called the z plane, meaning it's the xy coordinate system. And we take this point z, and we take neighboring points z1 and z2. So we saw that the condition for analyticity, did I get that right? Condition for the function being analytic is the derivative should be the same whether you approach from here to here or from here to here, right? The neighboring point can be anywhere. The answer should be the same. So let's take this as a neighboring point and then this as another neighboring point and see what happens. So we know that delta z is some delta x plus I times delta y. And delta zeta is delta psi plus I times delta eta. So if zeta of z is analytic, then d zeta dz should be the same for any direction of delta z. This can come from many directions depending on these two. So first let's take this point, and then let's take that point, and then we'll equate the two. So first let's take z, delta z equals delta x, which is this. And next we'll take delta z equals I delta y. So if you take the, so just to set ourselves up, the derivative d zeta dz is limit delta zeta over delta z as delta z goes to 0. So if delta z1 equals delta x, which is the first option, this derivative becomes d psi dx plus I times d eta dx. With the second option, delta z2 is I times delta y, and so d zeta dz is d psi over I dy plus I times d eta over I dy, which if you simplify, this becomes minus I d psi dy plus d eta dy. Now these two derivatives have to be the same. That means you can equate this real part with this real part and this imaginary part with this imaginary part, because they have to be the same. So Cauchy-Riemann conditions conditions for analyticity of zeta of z at point z is the two real parts have to be the same. And the two imaginary parts are the same. So d psi dx equals d eta dy, and d psi dy is minus d eta dx. So there are some important consequences. There are actually a few pages of that. And this is what helps us connect it with potential flow. So up to this time it's all some seemingly abstract stuff, but now we'll see how it connects to potential flow. So if the real and imaginary parts of a complex function satisfy the Cauchy-Riemann equations, right, which is this and this, then the function is an analytic function. These are all some rules and consequences. If once you satisfy these, you can say zeta of z is an analytic function. The second consequence is, and I think I have to show it together, is let's take the derivative of the first equation with x. So this will become d squared psi over dx squared, right? And the derivative of this with x is d squared eta over dx dy. And let's take the derivative of this with respect to y, and this will become d squared zeta over dy squared, and this is minus d squared eta dx dy. So what you see is that this happens, d squared zeta over d squared psi over dx squared is minus d squared psi over dy squared. Or in other words, Laplacian of psi equals 0. Psi satisfies Laplace's equation. And in a very similar way, we can show that eta also satisfies Laplace's equation. And that now starts to ring a bell, right? What satisfies Laplace's equation that we have seen before? Stream function and velocity potential. So stream function and velocity potential satisfy Laplace's equation, and they represent potential flow. Now we start to see some connection. In a similar way, the real and imaginary parts of a complex function also satisfy, of an analytic complex function satisfy Laplace's equation. And so in complex variables, these are called harmonic functions. There must be some reason for it. I don't know why it's called harmonic function, but it's called that. So these, both the real and imaginary parts are harmonic functions. In other words, they satisfy Laplace's equation. But they are not independent harmonic functions. So if one is specified, using Cauchy-Riemann equations, you can determine the other to within an arbitrary additive constant. So they are not just harmonic functions, they are called conjugate harmonic functions. These are just terms given. There must be a reason why they have been called these things. I don't know why they're called, but in papers, like even in, I think even in the paper on profile, where they're talking about the theory behind profile, you'll see these terms, conjugate harmonic functions. That's what it means. It means an analytic function whose real and imaginary parts are, satisfy Cauchy-Riemann equations. Now, another consequence of satisfying Cauchy-Riemann equations is if you take contour lines formed by psi equals constant, and those formed by eta equals constant, these contour lines always intersect each other at 90 degrees. So we saw these contour lines earlier, right? I said several pages back, I tried to graphically illustrate what is psi and what is eta. This one complex function, this is another complex function. Now, if these are analytic, they will intersect at 90 degrees everywhere. So it forms a mesh, and at every intersection, it's always 90 degrees. What does that remind you of? Does it remind you of something? Yeah, remember stream function and isopotential lines of constant velocity potential. At every intersection, they're always at 90 degrees. Okay. the fifth consequence is if zeta of z is analytic and if the derivative is not equal to 0, then it says that there is an inverse function. There exists an inverse function which is z as a function of zeta, and that is also analytic, and its derivative is given by z prime is 1 over zeta prime. Okay, so this is as long as the derivative zeta prime is not equal to 0. So a lot of these things are actually used when we go to mappings of flows, and so this helps us, as we'll see shortly, connect to potential flows. So the beauty of analytic functions is that the properties exhibited by the real and imaginary parts of an analytic function are identical to the properties exhibited by the velocity potential and stream function of a 2D incompressible irrotational flow. So this is what we call potential flow, or it's also called ideal flow, and vice versa. So you can take any potential flow, any ideal flow, and the stream function and velocity potential of that flow are really some analytic function of the xy coordinate, complex function z equals x plus iy. Okay. I was going to say something else. Yeah, so because this is, that book I talked about in the beginning, Karam Chetty's book, Principles of Ideal Fluid Aerodynamics, right? Ideal fluid is nothing but potential flow. So this book is actually, it's a thick book, but it's completely filled with potential flow theory. I mean, he connects it to viscous flow and real flows, but it's a book that talks about lots of different sorts of potential flow and everything. Most of it is aeronautical, so it's very useful for us. Okay, I have like 5 minutes or so. Let's talk about a few analytic functions. So some example analytic functions, and these are all analytic functions we'll use. A polynomial function is an analytic function just by nature. I mean, you can check it by seeing if it satisfies Cauchy-Riemann equations. But for now, we're just going to list them without actually showing each one. So if you have a0 plus a1z plus a2z squared and so on, where these are all complex numbers, complex constants, and n is positive, that's an analytic function. A rational function is also an analytic function as long as the denominator doesn't go to 0. So you have a complex polynomial function in the top divided by another complex polynomial function of z. That's analytic. Okay, so I think if you go and do a course on complex variables, maybe you'll go much deeper into all these things, but we don't need to. A power series likewise, where a n z to the power n. So this is a polynomial series, but it goes to infinity, right? N goes from 0 to infinity. Where a1, a2, a3 are all complex constants. This is also analytic within a region of convergence. And because a power series is analytic, we can take a lot of these kind of functions like exponential, e to the power z, sine of z, cosine of z, sine, hyperbolic cosine. These are all analytic because they're all essentially can be expressed as power series. I'm just going to list them, and I think for our purposes that's all we need. We'll just take it that somebody has actually gone and verified all these things. Then we come to this interesting function called logarithm of z. Right? So you can write z in polar coordinates, in polar form. This is same as, and if you look at my 3 pages of notes on review of complex variables, you'll see that. So this is z equals x plus iy, right? And this is x, and this is y, iy, I guess, real and imaginary. So a polar form of a complex variable is, you write it in terms of r and theta, and r times e to the power I theta is z. It's the same as this is x plus iy. The problem with this notation is that the theta is multi-valued. In other words, you can take this theta, and if you add 2 pi to it, you're going to get the same z, right? So theta is really some theta p plus 2 pi times k, where k is an integer. Because if you put k as 0, then it's just the main theta, theta p, which is the principal value. So p subscript is principal value. And then you can add many 2 pi's and you'll always come to the same point. So you can really write z as r e to the power I times theta p plus 2 pi k. And if you take the logarithm of this, log z is log of r plus I times theta p plus 2 pi k. So in other words, log z has multiple values that differ by multiples of 2 pi times I. And so these various values are called branches. Okay, so we'll just take a quick look at a graphical representation of this, and we'll come back to it later. So what does that mean? So if you attempt to draw log of z, right? So let's take the z plane, which is x and y, right? So this is a z plane. And let's take a point z. If you calculate log z from here and go around a contour like this and come back here, log z will come to the same value with which we started. But if you calculate log z and go around a contour like this and come back here, the log z will change by 2 pi I. And so if you go around 3 times, 4 times, it will change by that many 2 pi i's. So z equals 0 is called a branch point. So this is a kind of complicated shape, mind-bending shape, but it's kind of like a car parking deck in some ways. So in some parking decks you enter and you go around, you keep going to higher and higher levels. It's like a spiral helical staircase. So if you have a big road that's going in a helical shape and you're in one point of the road, if you don't cross the origin, if you just make a circle by walking or something, you will come back to the same place, right? But if you walk around the central pillar, you'll go up 1. And if you walk around the next pillar, you'll go up another. So log z is kind of like that. So this point is called a branch point. Does that remind you of something in aerodynamics? What's that? Stagnation. There might be a connection to stagnation, but that's not what I'm thinking about. Yeah, circulation, right? So if you take an airfoil, circulation is integral v dot dl. So if you do integral v dot dl around a contour here, circulation is 0, you'll come to the same thing. But if you take the circulation and go around like this, you'll go up by 1 circulation amount. And if you do that many times, your integral v dot dl will keep adding. But here, it will not add, right? So this is actually a connection this is a connection we'll make. But don't ask me how they thought about it. It's just, you have to, I guess, think differently for this. Anyway, we'll stop here and we'll resume in the next class.